Welcome to Eternal AC Education. In this session, you are going to learn Chapter 8, Iteration and Recursion. Content of this video is: what is invariant, what is loop invariant, and what is recursion. This is Chapter 8, Iteration and Recursion. So, as we know, iteration is a set of statement is going to be repeated many times. There are several problems which can be solved by doing same action repeatedly. Both iteration and recursion are algorithmic design techniques to execute the same action repeatedly. Note the point. Both iteration and recursion are algorithmic design techniques to execute the same action repeatedly. What is the use of repeating the same action again and again? Even though the action is the same, the state in which the action is executed is not the same. That means we may think that it is a repeated steps, but there is a thing that state which is going to be changed for each action. Each time we execute the action, the state changes. Therefore, the same action is repeatedly executed but in different states. So, what is the use of repeating the same statement? Even though the same set of instruction is going to be repeated but in different states. That state changes in such a way that process progresses to achieve the desired input-output relation. So here we are going to learn about iteration and recursion. The common property of iteration and recursion are both same actions are going to be repeated. That means it is going to execute a set of instruction or a step repeatedly. Iteration. In iteration, the loop body is repeatedly executed as long as the loop condition is true. So this is the important point. We may know that iteration is repeating a steps many times. How many times it is going to be repeated? Then there is a condition to decide how many times the steps is going to be repeated. Here there will be a condition, and if the condition is true, it will repeat, or else it will keep on repeating until the given condition is true. Each time the loop body is executed, the variables are updated. However, there is also a property of the variables which remains unchanged by the execution of loop body. Loop body means nothing, it's a set of instruction. This unchanging property is called the loop invariant. So we are going to see about what is loop body and what is variant and what is invariant property. Loop invariant is the key to construct and to reason about iterative algorithms. Then what about recursion? Recursion is another algorithmic design technique closely related to iteration but more powerful. So only thing is it's technically powerful than iteration. Using recursion, we can solve a problem with a given input by solving the same problem with a part of input and constructing a solution to the original problem from the solution to the partial input. We'll see with an example what is recursion. Now, we'll see what is invariance. Consider example program. UV equal to 2050. That means the variable u is having the value of 20 and v is having the value of 50. That means the starting location uv is 20, 50. Then u plus 5, v minus 5. So now 20 plus 5, it is going to be 25. 15 minus 5, it is going to be 10. So after assignment, but what do you observe about the value of the function u plus v? Before u plus v, that means first time it is 20 plus 15. Okay, so we'll have a statement as u plus v. So 20 plus 15, what is the value? 35. Okay, now there is a change u plus 5 and v minus 5. So the variable value is changed, but even though the value is changed, the statement for u plus v is again 25 plus 15, it is 35. Okay, so the assignment has not changed the value of u plus v. We say that u plus v is an invariant of the assignment. So why it is invariant means even the value of u and v is changed before and after, but the content of u plus v remains to be same. So the statement u plus v is an invariant, that means unchangeable, remains the same. We can annotate before and after statement with the invariant expression. So before u plus v it is 35, after the change it is also 35. We can say u plus v is an invariant, it is 35 before and after, or we can say u plus v equal to 35 is an invariant, it is true before and after. So when it remains to be same throughout the execution, before and after the state, then it is said to be invariant. Is it clear, children? Do you able to understand what is invariant? If a statement remains to be unchanged, and it is said to be invariant. If we execute the following statement, they are giving another example. See here, p comma c, 10 comma 9. So first it is 10 comma 9, then they are increasing the value p plus 1 and c plus 1. Then it is 11 plus 10. Then they are asking for a statement p minus c. First the value is 10 9. Okay, so 10 minus 9 1, it remains to 1. Again it is 11 and 10. So here also it is, the difference is 1, so that the p minus c equal to 1 is an invariant. So it is going to be the same value throughout the execution. In general, if an expression of a variable has the same value before and after an assignment, it is an invariant of the assignment. Let p of u comma v be an expression involving variables u and v, p of u v, where u comma v colon equal to e1 comma e2 is obtained from p of uv by replacing u by e1 and v by e2 simultaneously. This is an invariant assignment. So they have formed an equation based on this. So what is invariant? There is a statement or an expression which is going to be unchanged before and after. So that is said to be invariant. Then what is loop invariant? In a loop, if L is an invariant of the loop body B, then L is known as loop invariant. So what is it? We know invariant. What is loop invariant? In a loop, if L is an invariant of the loop body B, then L is known as loop invariant. While condition, they are executing L and L before and after. This L is going to be same. We'll see with an example. Loop invariant is true before the loop body and after the loop body each time. Since L is true at the start of the first iteration, L is true at the start of the loop, just before the loop. Since L is true at the end of the last iteration, that means these are the properties to set that a loop invariant. What are the four things? It should be true at start of the loop. It should be true at each iteration, start of each iteration, end of each iteration, and end of the loop. If a variable remains to be same before the loop, before the body of the loop, that means end of the iteration and end of the loop, then it is said to be loop invariant. So these are the locations said to be start of the loop, start of the iteration, end of the iteration, and end of the loop. Explain loop invariant is an important question. So how to construct a loop? Establish a loop invariant at the start of the loop. The loop body should update the variables so as to progress towards the end and maintain the loop invariant at the same time. When the loop ends, the termination conditions and the loop invariant should establish the input-output relationship. So the loop invariant is true in 4 crucial points in a loop. Here, a to the power n, okay? So 10 to the power 4, 5 to the power 3, 2 to the power 5. Here, a to the power n means a into up to n times. The a should be multiplied n times. So this is a specification of the algorithm. The algorithm name is power of a comma n. Input n is a positive integer. Then the expected output is a to the power n. If p comma I equal to 1 comma 0. So the variable p is having the value 1 and I is having the value 0. While I not equal to n. The loop has to execute until the value of I is not equal to n. Imagine that n is having a value of 5. Here it is 2 comma 5, 2 to the power 5. So the n value is 5. So the loop invariant is p equal to a to the power I. We'll see in steps. See here, first iteration, 0 iteration, the value in p is 1. How it comes? See here, 1 comma 0. Okay, then I is 0. So 2 to the power 0. Next iteration it is 1. P value increases to 2. So 2 to the power 1. So each time the variable is taken, each row shows the values of the two variables p and I at end of the iteration. P equal to a to the power I is true at the start of the loop and remains true in each row, and it is a loop invariant. See here, a to the power I. So what is the value of a? 2. I, it's going to be the value of power. Here it is 2 to the power 0, 2 to the power 1, 2 to the power 2. Each time the value in I and the value in a remains as the expression given. The value of a to the power 1 is still true, but I equal to 5, therefore a to the power 5. In general, when the loop ends, p equal to a to the power n. Thus, we have verified that power of a to the power n satisfies its specification. Next concept is recursion. So, recursion is an algorithm design technique closely related to induction. It is similar to iteration but more powerful. Using recursion, we can solve a problem with a given input by solving the instance of the problem with a part of the input. What is the meaning? See this example. Customers are waiting in the line at a counter. The man at the counter wants to know how many customers are waiting in the line. So, first person, second, third, one. That means come here, one. So first person, 1 plus 1. Then here it is 2 plus 1. 2 people plus 1 person. Here it is 3 person plus 1. And here it is 4. So each length is added. Single small length, small distance is added to get the final result. Instead of counting the length himself, he asked customer A for the length of the line with him at the head. Customer A asked customer B for the length of the line with customer B at the head. And so, when the query reaches the last customer in the line, E, since there is no one behind him, he replies 1 to D, who asked him. So D replies us 1 plus 1, that is 2. C replies us 2 plus 1, that means 3 persons. Then 3 plus 1, 4 persons. So A replies 1 plus 4, that is 5 persons in the counter. So the counting is splitted and it is done repeatedly also. Let us represent the sequence of 5 customers A, B, C, D and E as the 5 variables. The problem is to calculate the length of the sequence. Let us name our solver length. If we pass a sequence as input, the solver length should output the length of the sequence. That means a length of A, B, C, D equal to 5. The solver length breaks the sequence into its first customer and rest of the sequence. That means A, B, C, D is now B, C, D, E. Likewise, each time it is subdivided. Each solver reduces the size of the input by 1 and passes it on to the subsolver, resulting in 5 solvers, as there are 5 people. This continues until the input received by the solver is small enough to output the solution directly. The last solver received E as input. Since E is small enough, the solver outputs the length of E as immediately 1. So this is the explanation. He is saying 1 and he is saying 1 plus 1. He is saying 2 plus 1. Here he is saying 3 plus 1 and here he says 4 plus 1. To solve problem recursively, the solver reduces the problem to subproblems and calls another instance of the solver known as subsolver to solve the subproblem. So simply, recursion is going to be divided into subproblem. The beauty is the first subproblem should be cleared and the result is added to the another subproblem and it is cleared. Both the results are added to another subproblem. Likewise, it is doing its execution. The input size to a subproblem is smaller than input size to the original problem. When the solver calls a subsolver, it is known as recursive call. The magic of recursion allows the solver to assume that the subsolver outputs the solution to the subproblem. Then from the solution to the subproblem, that means it's keeping repeatedly. As the sub-solvers go on reducing the problem into sub-problems of smaller size, eventually the sub-problem becomes small enough to be solved directly without recursion. So the recursion is having two cases. One is base, another one is recursion step. Base means the problem size is small enough to be solved directly. Output the solution. There must be at least one base case. Next, recursion step. The problem size is not small enough. Deconstruct the problem into sub-problem, strictly smaller in size than the given problem. Call the subsolver to solve the sub-problem. Assume that the subsolver outputs the solution to the sub-problem. Construct the solution of the given problem. A big solver, then there is a sub-solver and the solution, and another subsolver and the solution. Likewise, it is going to be executed. Recursive problem solving. Each solver should test the size of the input. If the size is small enough, the solver should output the solution to the problem directly. If the size is not small enough, the solver should reduce the size of the input and call a subsolver to solve the problem into reduced input. We'll see the example for this. Recursive algorithm for length of sequence can be written as, so length of S, input S, output length of the S. This is the specification name, algorithm name. If S has one customer, base is 1, else 1 plus length of the tiles. Do you understand this? Actually they will say 1, next 1 plus 2, 1 plus 3, like that. Design a recursive algorithm to compute a to the power n. How to do this? Base class is 1, that is if n equal to 0. Otherwise, that means if the power is 0 means always the value remains to be 1, that is a to the power 0 is 1. So the n value is 0 means then the base is 1, or else a into a to the power minus 1. This is the recursive step. So see here, 2 to the power 5 means first step is 2 to the power 4, a minus 1, am I right? So a into a to the power n minus 1. So 2 to the power 4, then 2 to the power 3. The n value is getting reduced. 2 into 2 to the power 4, then 2 into 2 into 2 to the power 3. Do you understand? 2 means this a value, okay? So first point 2 into 2 to the power 4. Next 2 into 2 into 2 to the power 3. Then 2 into 2 into 2 to the power 2. Likewise it is coming. So the algorithm name is power of a to the power n. Input as n is an integer, n is greater than or equal to 0. And then expected output is a to the power n. First, if the value of n is 0, then this is the base class. That means one execution, that is 1. Here the value is 1. Sometimes the value may change, but the requirement is there must be a base case. Next, if it is not like the base case, then it goes for the recursion step. That is a into power of a to the power n minus 1. So in this chapter we have seen iteration, repeated steps, the 2 steps of evaluating a condition and executing a statement as long as the condition is true, that is iteration. Then an expression involving variables which remains unchanged by an assignment to one of these variables is called invariant of the assignment. An invariant for a loop body is known as loop invariant. If it is a loop invariant, it should satisfy 4 conditions. One is, it must be true start of the loop, start of the iteration, end of the iteration, then end of the loop. Then recursion. Recursion must have at least one base case and recursion steps. So the recursion steps breaks the problem into sub-problems of smaller size. Assume solution for sub-problems are given by the recursive calls. So a problem is divided into sub-problem, and a sub-problem is going to give a solution, and again a solution. Likewise, it is going to be get the final solution. In recursion, the size of the input to a sub-problem must be strictly smaller than the size of the given input. So these things we discussed in this chapter. So that's all for this session. Thank you. Have a good day.